The Class 318 is a British Electric Multiple Unit, EMU, built in 1985 by British Rail Engineering Limited, or BREL. They were originally used for Ayrshire Coastline Express services, but now can be found operating commuter services on the Cathcart Circle, Paisley Canal, Argyll, North Clyde, and the West Coast Main Lines down to Lanark. On the inside, they're just like any other commuter train, but what I want to focus on is what's going on under the floor. How do these marvels of British engineering work? In this video, I'll explain every aspect of how these work the best I can, and nearly everything I'll say also applies to the very similar Class 320, however I'll explain the differences later on. Let's start with the train as a whole. It's an electric multiple unit, meaning that all the machinery is under the floor and a locomotive is not required to pull the train. This also allows the train to be driven from both ends, making for a quick turnaround at terminus stations. The unit consists of 3 coaches which, as well as carrying passengers, each has its own role to play to make the train work, although if required, 2 units can be coupled together to form a 6-car train. There are 4 sets of exterior doors per coach, 2 on each side, and these are located at the 1/3 and 2/3 positions, meaning that they split the coach into thirds, separated by each door vestibule. This configuration is best suited for commuter and regional trains which stop often. These doors are of the slide-in type, meaning they slide into the side of the bodywork of the train, instead of the usual plug doors which pop out first before sliding. The doors are operated pneumatically, using compressed air to move a piston inside a cylinder to open or close the doors. To ensure the doors stay closed or open, there is a constant air pressure applied to the cylinders. The cylinders used are double-acting cylinders, meaning that they can be pushed in both directions by compressed air. The internal gangway doors are just regular slam doors instead of power-operated sliding doors. Not much to say about these, but there's far less to go wrong. 334. The train has electric heating, which works absolute wonders in the winter. But for the summer, it has air conditioning in the form of opening windows, which keep it at a steady 1 to 2 degrees above the outside temperature. Now, we will go coach by coach from one end of the train to the other. We will start with the DTSL, the Driving Trailer Standard Lavatory, which means it has a driving cab, the wheels aren't driven, they're just trailer wheels, with standard class seating, and it has a lavatory. The driver's cab has its own section with the seat on the left side. This is so that the driver can see signals and line-side signs better. These cabs used to have end gangways on them, but these were removed as they were deemed unnecessary and to give the driver a bit more space. This would have looked like the 156, which still has its end gangways. The train is driven by 3 different handles. The reverser determines the direction of travel and spends the vast majority of the time in the forwards position. The brake and accelerator are on separate handles here, which gives the driver a little bit more control when starting on a steep uphill gradient and helps prevent rolling back. This is done by having a small amount of braking applied and a small amount of power at the same time, then releasing the brakes and increasing the power. The train's brakes, just like all trains, are pneumatic and work by having a pipe that runs the entire length of the train and connects to the brake pads on each wheel. When the pressure in the brake pipe is high, the brakes are released. To apply the brakes, the pressure in the brake pipe is decreased. This is a fail-safe, as if there's damage to the brake pipe or the train becomes separated, all air pressure in the brake pipe is lost and the brakes come on full force. This system is known as a Westinghouse brake, which was a braking system developed by George Westinghouse, which was very advanced for its time. However, more modern trains don't have it, as the fail-safe aspect is controlled electrically. Moving backwards through the coach past the very comfortable seats, we get to the lavatory. This does have a retention tank under the train, so there won't be any unwanted tomatoes growing on the tracks as a result of any unwanted fertilizer, shall we say. It's also fully wheelchair accessible. Next, we move to the PMSO, Power Motor Standard Open, coach. As it says on the tin, this coach contains the power collector and transformer, the traction motors, and features a standard class configuration with no compartments. All the high power equipment is contained within this one coach, which negates the need for running high voltage and current cables through the train. The power is collected from the overhead wires by a pantograph, which is sprung so that it can remain in contact with the wires when they change height. The wires in Britain are always energized at 25 kilovolts AC at 50 Hz, which is ideal for the amount of power a train requires, but not ideal for any person or thing that comes in contact with them. This power is sent to a transformer, which steps the voltage down to two separate voltages, a higher voltage for powering the traction motors and a lower voltage for powering the train's auxiliary equipment, such as the lights, heating and air compressor. There are 4 traction motors on the 318, one for each axle of the PMSO, and these are DC motors, which will require the AC power from the transformer to be rectified into DC. This is done by having 4 diodes and a capacitor in this configuration. Again, go to Electroboom's channel for more information, link in the description. The DC motors are controlled by PWM, which is pulse width modulation, which is when the power to them is turned on and off really quickly at a set frequency, with the amount of on time being varied. This is done by having a GTO, or gate turn-off thyristor, being controlled by an analog circuit. The pulsing frequency is controlled directly from the 50 Hz main supply, which negates the need for any artificial signal generation. This helps as well because the way the GTO thyristor works is it's basically an electronic switch, and if you apply a positive voltage to the gate, it will switch on, and to switch it off, you apply a negative gate voltage. And the continuously changing polarity of the main supply is perfect for this. There are capacitors within the gate control circuit which are connected and disconnected as needed in order to vary the pulse width. These capacitors have to have a very low capacitance in order to fully discharge before the next 50 Hz cycle happens. This is why you can hear an additional 50 Hz hum from the motors when they start up above the 50 Hz hum already coming from the transformer. Also, I think these trains sound great when accelerating. They sound especially great in the underground section. As well as being used to accelerate the train, the motors also do regenerative braking. This is when the kinetic energy of the train is converted to electrical energy by the train's motors. All motors can work in both ways like this. The generated power is fed back through the transformer and back into the overhead wires, which can be used to power other trains further down the line, and reduce the overall power consumption by the railways, and also reduces wear on the brake pads. People often think this technology is a recent development, but train manufacturers have been doing it for years. Walking through the gangway again, we come to the DTSO, or Driving Trailer Standard Open Vehicle, where we can find 2 pieces of noisy equipment under the floor. The air compressor monitors the pressure in the main air reservoir, which supplies the train's pneumatic systems with compressed air. When the air pressure gets too low, the motor on the compressor starts up and pumps more air into the main reservoir by use of a spiral system like this, which traps air in these gaps in order to compress it. When the desired pressure is reached, the motor then shuts off again. The air compressor is what makes this sound. And finally, we get to the Spirax valve. This is again something which is unique to older trains and is less common nowadays. This device continuously removes moisture from the main air reservoir periodically, which is necessary as the water would otherwise get into the valves and cause them to rust, which isn't good. The Spirax valve is what makes this distinctive sound. As previously mentioned, the Class 318 is very similar to the Class 320. The only differences between the two are the fact that the 318 and the 320/3 have a max speed of 90 miles an hour, however the 320/4 can reach 100. The 320 also has a slightly different cab with a more compact design, although the controls are still the same. However, both units have the same acceleration of 1.2 miles an hour per second, they both have 1,300 horsepower, and the two types can be coupled together if needed. So that was quite a lot of information, so feel free to ask any technical questions at all in the comments below, and I'll try and answer as many of them as possible. If you're interested, I can make this into a series, so let me know which train you want me to cover next. In the meantime, thanks for watching and enjoy the outtakes.
I feel like a bit of harmonica on a really old train. I feel like a bit of harmonica while on a 318. Nothing like a bit of harmonica on a 318.
Now we will go coach to. Oh, fuck's sake. When the air oh god, no, I'm gonna have to start that one again, aren't I? As previously. Okay, some water might be a good idea here.